Hey guys, on this lesson we are going to be studying heat during phase changes. We'll talk about some theory for heat of fusion and for heat of vaporization, and also the mathematics of the heat of fusion and for vaporization. You will need a calculator, so if you don't have one with you, go get it, and you'll also need a reference table. There is a homework associated with this lesson. It's going to be just a few questions on pages 65 and 66. We'll do that in class tomorrow. And I need you to copy down this aim as well as the homework on a separate piece of paper for classwork in your binder. And underneath that, you need to have these do now questions. This equation looks a little funny, so I will rewrite it for you. So there it is. Just copy down these questions on your separate paper for classwork. All right, so the theory of heat of fusion. Firstly, in Unit 5, we use fusion to mean melting or freezing. And we cannot use Q equals MCAT during phase changes because temperature is constant during phase changes, and therefore delta T would be 0. And the definition for heat of fusion, you may remember, is the amount of heat required to melt 1 gram of a substance at STP. Naturally, different substances being made of different atoms would have different values for heat of fusion, but the value for water you'll be able to find on your reference table, and that is 334 joules per gram. The heat of fusion, meaning that the 334 joules for every gram of substance, that is being spent on increasing the potential energy of the particles in the substance. Because when you're going through fusion, that's like melting. So you're separating the particles of a solid into the particles of a liquid, and you're increasing ever so slightly the distance between those particles. And that requires energy to do that since it's going into potential energy. So during fusion, one of the things that changes is potential energy. The potential energy is going up if it's melting, the potential energy is going down if it's freezing, and what remains constant is temperature. Temperature does not change during the fusion process. All right, so we need to talk some math right now for heat of fusion. This is an example question that you would see. How many joules are required to melt 255 grams of ice at 0 Celsius? It has a very similar structure to the questions that we solved yesterday because it's asking for joules, which is a value for Q, and it gives you grams, which is a value for mass, and it even says ice, so we know that it's water. And it gives you a temperature as well, but I'm going to give you a note of caution, which is we said that temperature remains constant during heat of fusion. So if it gives you a temperature like this, it's not part of the math. They're just telling you that it's at its freezing point and it's going to stay at that temperature. They're not trying to ask you to use that value in any equation. And since it's ice, we know the value of HF. It was on our reference table. So we have a Q, an M, and an HF. So the equation that we need to use is Q equals MHF. This is also on your reference table on the back page, table T, but this is the equation that you would use for melting and freezing. I'm going to identify the things we know and the things we don't know. What we do know so far is the mass, and we also know the HF. The mass is 255 grams. And the HF is 334 joules per gram. What we don't know is Q, and that's heat. So if we start with this equation, Q equals MHF, and we substitute known values into this equation, it's already arranged for us, so I'll just leave it like Q, like this, with Q in front. The mass is 255, and the HF is 334. So I've substituted, and the last step is just to solve. So I got 85,170 joules. Remember, joule is the unit for Q. And it's a very large number, so I encourage the practice of writing this in other ways, such as in kilojoules and in scientific notation. I'm going to do those one at a time. Remember, when you convert from joules to kilojoules, you divide by 1,000. And when you do scientific notation, you can only have one digit to the left of the decimal. So those are the values I would use. All right, so heat of vaporization is similar to heat of fusion, except that it is the amount of heat required to boil or condense 1 gram of a substance at STP. So the symbol and value for the heat of vaporization, the symbol is going to be HV, and the value is 2260 joules per gram, and I got that from the reference table, table B. The heat of vaporization is being spent on potential energy, just as heat of fusion is being spent on potential energy. So if you're putting energy in to vaporize something, that energy is going into separating the particles, which increases the potential energy. So the heat of vaporization, being 2260, is quite a bit larger than the heat of fusion, which I'll just add in over here as 334 joules per gram. It's much, much, much larger. The reason why it's so much larger is because of this idea, that increase in potential energy is separating particles. When you separate particles from a solid to a liquid, you're separating them just a little bit, so it only requires this much energy. But when you separate particles from liquid to a gas, you're separating them an enormous amount, an almost infinite distance, and therefore the amount of energy required to do that is going to be significantly larger. So the way I explained that was the liquid-gas transition requires larger change in potential energy than the solid to liquid transition, or visually you can think of it this way. Solid to liquid is only 334, but liquid to gas is a larger change, so it's 2260 joules per gram. During vaporization, things that change are if you are boiling, potential energy increases. If you're condensing, potential energy decreases. But what remains constant is that boiling is a phase change, so the temperature remains constant. All right, so let's do some math of the heat of vaporization. This style of question you've seen before. It reads, how many joules of energy are required to vaporize 423 grams of water at 100 Celsius and 1 atmosphere? So let's label some stuff. When they say how many joules, they're referring to the quantity Q of energy are required to vaporize 423 grams, which is a mass, of water. So they're telling me that I'm allowed to use the value for HV on my reference table at 100 Celsius and 1 atmosphere. This sounds like information that you should use, but in actuality, it's just telling you that it's at a constant set of properties, and those things aren't going to be changing, and they're not going to enter into your calculations. The things that you know here are the mass, which is 423 grams, and the heat of vaporization for water, which is 2260 joules per gram. We do not know at this point Q, which is the amount of heat. So the equation is Q equals mHV, which is on the back page of your reference table. And if I substitute in values that I do know, it's going to be 423 grams for the mass, and for the HV, it'll be 2260 joules per gram. All I need to do now is solve and assign the correct units. And I get 955,980 joules. I do encourage you in the next step to convert this into kilojoules by dividing by 1,000. And finally, in the third step, I encourage you to convert this into scientific notation, keeping in mind that you should only have one digit to the left of the decimal. It's really good to do those conversions when the number is very large. All right. right, guys, you have made it to the pair up. I just need you to copy down these questions underneath the homework, aim, and do now on the classwork page of your notes for this lesson, and follow it up with these summary questions. These look like ones, but they are actually supposed to be L's for liquid. And everything else looks pretty good. So copy down these questions as the final section for classwork this lesson. Thank you for watching.